Hello viewers, Wagdara now taking you through today's tutorial for A-Level Physics Paper 2. So in this video, I'm going to go through the marking guide of Senior 5 beginning of Term 3 exam of Physics Paper 2. So the question paper was already sent a few days before. So I believe by now you have already tried out the questions and you are ready to mark yourself and make corrections and also check your progress. So where necessary, those constants would be used. So you start with question 1. So question 1, A Roman 1 says, state the laws of refraction of light. So one of the laws is that the angle of incidence is equal to the angle of refraction. Then the second law is that the incident ray, refracted ray, and the normal at the point of incidence all lie on the same plane. Note this word on. So that was Roman 1. Now we shall go to Roman 2. So Roman 2 said, state 4 characteristics of images formed by convex mirrors. So your common answer that the images formed by convex mirrors are 1. Virtual, 2. Upright, 3. Diminished, and 4. Formed between the principal focus and the pole of the mirror. So here 1 mark for each law, half a mark for each characteristic. So now we shall go to part B. So part B said, Roman 1, explain why parabolic mirrors are preferred to spherical mirrors in headlamps. So a parabolic mirror reflects all the light rays from a light source at its focus as a perfectly parallel beam. Know that word, perfectly parallel beam. So what does that mean? It means that the intensity of the reflected beam is practically undiminished at longer distances from the reflector. What about a concave mirror? For a concave mirror, the light source placed at its focus produces a parallel beam only close to the axis. What does that mean? It means that rays reflected from points far away from the principal axis give rise to a divergent beam. So when the beam is divergent, what does that mean? It means that the intensity reduces the intensity of the reflected beam at longer distances of the reflector. So basically that is why parabolic mirrors are used, because parabolic mirrors the intensity is undiminished, but for concave mirrors the intensity reduces. So half a mark for this, half a mark for this, half a mark for this divergent beam, and half a mark for intensity reducing. So now we shall go to part B, Roman 2. So part B, Roman 2 says, describe how the focal length of a convex mirror can be determined using a converging lens. So such questions are easily done by making a sketch. So let's first put up a setup in form of a sketch to help us easily describe the setup of the apparatus. So we have that object screen with an illuminated object. Then we shall have here a converging lens or a convex lens. Then we have an image screen on that side, which is S2. So that setup, we shall come and say that a convex lens L1 is placed at a distance greater than its focal length. So note this word, greater than its focal length. The reason is to produce a real image. So greater than its focal length, this word has to be there from the illuminated object, and the apparatus is set up as shown. So this has to be there, because if it is less than the focal length, the image will not be real. So you come and say that this is because the convex lens, to form a real image, the object must be behind the principal focus. After that, we shall say that the image screen S2 is adjusted until a sharp image is formed on it. The distance x between L1 and S2 is measured. This distance x is measured between the lens and the image screen. So before we go to the next slide, let's see marks for this slide. So have a mark for the correct setup, have a mark for this word to be this word seen, and have a mark for measuring distance x. So after that, we shall say that the convex mirror, whose focal length f is required, is placed coaxially between L1 and S2. So in between this L1 and S2, we are going to put the convex mirror. Then we shall say that the mirror is adjusted until a sharp image is focused on S1. Remember that mirror will reflect light rays back up to the where they came from. So a sharp image will be focused on S1, which is the object screen, adjacent to the object, and the distance y between L1 and the mirror is measured. The focal length is therefore calculated from this formula that f is equal to x minus y over 2. Now here they didn't tell us to derive this formula, they only told us to describe an experiment, so there is no need to derive how this f comes about. So just quote it, and that is all. So now we shall go to part C. So part C, they give us this diagram, and they say that show that a ray that undergoes two successive refractions on two plane mirrors inclined at an angle beta suffers a deviation d, which is 2 beta. So the first thing to do is to redraw the diagram which was given, because we have to put the glancing angles to help us get the required proof. So that is what was given. The first thing to do is to put the glancing angle at this first reflection, which is theta. Now this glancing angle is the same as this one, and it's also the same as this if you extend this line. What about for this second reflection? The glancing angle is alpha, so this alpha is the same as this alpha, and also the same as this alpha. Now with that diagram, we can go ahead and answer and get what they wanted. So let's see marks for this slide. So that is M1 for this rearrangement, putting a convex mirror in between the lens and the image screen. Then half a mark, then half a mark for getting a distance y, and half a mark for the expression of focal length. So here I shall say that suppose the glancing angles at x and y are theta and alpha respectively. It implies that from triangle xyz, alpha is equal to theta plus beta. So when you come at this angle, this triangle xyz, this alpha, remember we have a property that one exterior angle is equal to the sum of two opposite interior angles. So that means that this alpha is equal to theta plus beta. Therefore, when I make beta the subject, beta will be equal to alpha minus theta. The deviation produced by refraction at x is 2 theta clockwise, and that at y is 2 alpha anti-clockwise. So let's see that. So at x, the deviation is, originally the ray was in this direction, so the deviation is from this original path up to the new path, and I think we realize that it is clockwise, and the angle is 2 theta. But for this one, it would originally here, so it has deviated up to this, so I think we realize that it is anti-clockwise and the angle is 2 alpha. So that is what they meant. Therefore, total deviation in anti-clockwise direction, it means that anti-clockwise will be positive and clockwise will be negative. Therefore, you come here and put your anti-clockwise as positive and clockwise as negative. 2 is common, I can factorize it out to come up with alpha minus theta. But I already know that alpha minus theta is beta, therefore I come and say that but beta is equal to alpha minus theta, therefore the total deviation will be to beta, which was required. So have a mark for the glancing angles, have a mark for this geometry, have a mark for this deviation at x, and have a mark for the deviation at y, have a mark for this total deviation substitution, and have a mark for the required expression. So now we shall go to part D. So part D, Roman 1 says, use a geometrical ray diagram to show relationship between the focal length f and the radius of curvature r of a convex mirror, and they said state clearly the assumptions made in the derivation. So they wanted the expression of relating focal length and radius of curvature of a convex mirror, but they said we use a ray diagram. So first we shall draw the principal axis, then the mirror, and show the principal focus and the center of curvature. So this is the principal axis, this is the mirror, this is the principal focus, this is the center of curvature, and this is the pole of the mirror. So we shall show a ray AB parallel to the mirror. So this is the symbol for the mirror. So this ray will be reflected, but for it to be reflected, we shall have to remember that angle of reflection is equal to the angle of incidence. So in this case, this will be the angle of incidence, because this line through the center of curvature will be normal to the mirror. Remember, the mirror is curved, only that this is a symbol, but it's curved, therefore implying that this angle will be 90, meaning that this is now the normal. Now at the normal, it implies that this angle of incidence will be equal to the angle of reflection, therefore we shall draw our reflected ray so that this angle is the same as that angle, and it appears to come from the principal focus. So you come and say that if this is alpha, it implies that this is also alpha. Then also if this is alpha, it implies that this is also alpha. Why? Because vertically opposite angles. Then also if this is alpha, it implies that this is also alpha. Why? Corresponding angles. Then if this and this is alpha, then this will be 2 alpha, because one exterior angle is equal to the sum of 2 opposite interior angles. So this plus this is 2 alpha. That's what will be here. So the distance between FP is focal length, and between C and P is R, which is the radius of curvature. So we shall come here and say that a ray per AB parallel and close to the principal axis is reflected to appear coming from the principal focus. As you can see it here, it appears to come from this principal focus F. That means that FP is the focal length. Then if C is the center of curvature of the mirror, then BC is the normal at B, and CP is the radius of curvature, which is R. So that's what I was telling you, that this line is the normal at B. So assuming that alpha is a small angle expressed in radians, what happens? So before we see what happens, let's see marks for this slide. So this for the correct diagram, this for identifying the focal length, this for identifying the radius of curvature on the diagram. So assuming that alpha is a small angle expressed in radians, it implies that alpha approximates to tan alpha and 2 alpha approximates to tan 2 alpha. So we shall go back on our diagram and we see that what tan alpha is. So tan alpha will be BP over CP. So when you go here, tan alpha is opposite over adjacent. Opposite is BP and adjacent is CP. But for tan 2 alpha, the opposite is BP, but the adjacent is FP or PF. That is why you see here that tan 2 alpha is BP over FP. Now next we are going to substitute for alpha, and when we substitute for alpha we shall come up with that. So where is that coming from? We know that this is equal to that, therefore, and we know that alpha is equal to this. So I'm going to bring this one and put it here to get 2 times BP over CP, and is equal to BP over FP, which is that. So this and this cancels. So you realize that when I cross multiply, FP will be equal to 2 times FP will be equal to CP. That is why they use CP equal to 2FP. But you already saw on our diagram that CP is R and FP is F. Therefore, this is the required relation. So now we shall go to Roman 2. So Roman 2 says, state 2 uses of concave mirrors. So one, we shall say that they are used in car head lamps and in searchlights to produce parallel beams of light. Then 2, we shall say that they are used by dentists as magnifying mirrors for magnification so as to examine the patient's teeth. Then 3, we shall say that they can be used as solar concentrators. Then 4, we shall say that they can be used in astronomical telescopes, refracting type of astronomical telescopes, to collect enough light rays that can be used to view astronomical bodies. The next we shall say that they can be used as shaving mirrors because they magnify the object. The next we shall say that they are used in projectors to collect light that would be lost. So here, half a mark for this assumption, half a mark for this substitution, half a mark for the relation. Here, any two, you give half a mark for each, and that will be 1 mark. So now we shall go to part E. So part E says a concave mirror of radius of curvature 25 centimeters faces a convex mirror of radius of curvature 20 centimeters and is 30 centimeters from it. So the distance between the two mirrors is 30 centimeters. If a real object is placed midway, you know that word midway, between the mirrors, find Roman 1 the position and nature of the image formed by reflection, first at the concave mirror and then at the convex mirror. So here we have to use the mirror formula. So for the concave mirror, we know that radius of curvature was given as 25, and we know that focal length is half radius of curvature, which will be 12.5, and the object distance, remember it was midway, meaning that it's halfway. So since the distance between the two mirrors was 30, halfway will be half of 30, which is 15 centimeters. So now that I have F and U, it means that V is the only unknown, so I'll write my mirror formula where V is on one side and F and U are on the other side. So that gives me 1 over V equal to 1 over F minus 1 over U. So I'll substitute for F, substitute for U to come up with 1 over 75. But this is the reciprocal of V. Therefore, V will be equal to 75. Then from there, remember that the image formed by the concave mirror acts as a virtual object with respect to the convex mirror. What does that mean? It means that now the image becomes the object to the convex mirror. Therefore, for the convex mirror, radius of curvature is negative, therefore focal length will also be negative 10 because radius was negative 20 centimeters. Then the object distance will be negative because it is now virtual, negative of the remainder. So 75 minus 30 will give you negative 45. Now I come and use mirror formula still to come up with 1 over F is that, U is that. Therefore 1 over V is negative 7 over 90, meaning that V is the reciprocal. But in physics we are not allowed to leave the answer in fraction form. Therefore you reduce it to become negative 12.86 centimeters. So always remember, in math it is okay to leave an answer in fraction form, but in physics it is not okay. Therefore the final image is virtual because this is negative. Remember they told us to also get the nature. So half a mark for this substitution, half a mark for that, half a mark for this, half a mark for that. So now we shall go to Roman 2. So for Roman 2, they say that draw a sketch red diagram for the action in Roman 1 above. So the first thing to do is to set up the mirrors, the two mirrors facing each other. So this is the principal focus, sorry, the principal axis. This is the first mirror and this is the second mirror. So this is the converging mirror, diverging mirror. The distance apart was 30 centimeters, and there was an object placed in between at the midpoint, so the distance is 15 centimeters. Then refraction is first at this one, so it will come and go there, the ray will come and go there. Then from here it goes to this other mirror. Now this one will appear to be at this point, so in absence of this mirror, this ray would have continued up to this point, so that will becomes our image 1. And here we used 45 because the total was 75, but 30 is already here, so the remaining part will be 45. Now this image is what acts as the object of this second mirror. That means that at this point there will be a refraction this side, and that ray will appear to come from this point, and this will be our second image, or the final image, where the image distance is 12.86. So basically that is what they wanted you to draw. Remember, arrows must be seen and in the correct direction. So now we shall go to Roman 3. So Roman 3 says, calculate the magnification produced by the above arrangement. So in this case they want the total magnification. Total magnification is the product of the individual magnification. So M will be equal to M1 times M2. So M1 is for the first mirror and M2 is for the second mirror. So for the first mirror, image was 75 and object was 15. Second mirror, image distance was negative 12.86 and object was negative 45. So when I multiply the two, I'll come up with 1.43 as the magnification. So here I have a mark for all these arrows and have a mark for these dotted lines. So I think you realize that these dotted lines, they don't have any arrow on them. Then have a mark for this substitution and have a mark for the output. So that was question 1. Now we shall go to question 2. Question 2, part A, Roman 1 says, define the term refractive index and critical angle of a material. Then Roman 2 says, state the laws of refraction of light. So you come here and say that refractive index of a material is the constant ratio, know this word, constant ratio of sine of angle of incidence to sine of angle of refraction for a ray of light propagating from a vacuum to a given medium. Note the order is that from vacuum to a given medium. You shouldn't interchange. Then what about critical angle? So critical angle is the angle of incidence in the denser medium, for which the angle of refraction in the adjoining less dense medium is 90. So note the order. This angle of incidence is in the denser medium and this 90 is in the less dense medium. So you don't change the order still. Then 2, they wanted the laws of refraction. So the first one, we shall say that the incident ray, refracted ray, and the normal at the point of incidence all lie on the same plane. Then 2, we shall say that for a given pair of optical media, the ratio of sine of angle of incidence to sine of angle of refraction is a constant. So yeah, 1 mark for this definition, 1 mark for this definition, and 1 mark for each law. So now we shall go to part B. So part B says, show that for a ray traveling from a medium of refractive index n1 to a medium of refractive index n2, the critical angle is given by C equal to arc sine n2 over n1. So in the question I had sent, it was the reverse, so you make that correction. So the first thing to do is to make a sketch of that ray. So we have two mediums, medium 1 and medium 2. In medium 1 there is a critical angle C, and medium 2 it glazes the surface. Therefore, taking Snell's law at O, we shall come and say that N1 sine C is equal to N2 sine 90. But we know that sine 90 is equal to 1, therefore sine C will be equal to N2 over N1, implying that C is equal to arc sine N2 over N1. So now we shall go to part C. Part C says, a cylindrical tank contains two transparent immiscible liquids. Liquid 1 of refractive index 1.3 is of depth 10 centimeters, and liquid 2 of refractive index 1.45 is of depth 8 centimeters. Determine the apparent position of the bottom below the surface of the upper liquid. So still here there was a correction made, because here in the question I sent, here there was the word displacement, which is not supposed to be there. So they only wanted apparent position. So when they want the apparent position, we just say that we just use T over N, where T is the thickness and N is the refractive index. So thickness for the first one was 10 centimeters, refractive index was 1.3. Thickness for the second one was 8 centimeters, refractive index was 1.45. Therefore the output will be 7.8736 centimeters, and that was the apparent position they wanted. So now we shall go to part D. So part D says, the figure below shows a ray of light traveling across parallel-sided media 1, 2, and 3, which is this. So given that medium 1 is vacuum, show that the refractive indices are related by n of O from 2 to 3 equal to n3 over n2. So for a ray moving from medium 2 to medium 3, n2 to 3 will be equal to sine r1 over sine r2. So when you go back to this diagram, from medium 2 to medium 3, it means that r1 is the angle of incidence and r2 is the angle of refraction. Therefore, refractive index is incidence of sine I over sine r, therefore it will become sine r1 over sine r2. So that is where this expression is coming from. What about taking Snell's law at the interface between medium 1 and medium 2? We shall come up with n2 sine r1 equal to n3 sine r2. So when you go back here, taking Snell's law at this point, it means that n2 sine r1 is equal to n3 sine r2. Therefore, when in this equation 1, r1 is up, sine r1 is up, so what I would need to do is to bring this one this side and this one the other side. So when I do that, I'll come up with sine r1 over sine r2 equal to n3 over n2. Now after that, you realize that this one and this one are the same. So what I'm going to do, I'm going to substitute equation 2 into 1 to come up with this expression which is required. So half a mark for taking Snell's law for this part medium, and also for this medium 1 mark. Then the required expression, that's also 1 mark. Starting the formula for total apparent depth is 1 mark. Substituting is 1 mark, and output is 1 mark. This one is also 1 mark for definition of refractive index. Then also Snell's law 1 mark, and substituting 1 mark. So now we shall go to part E. So part E Roman 1 says, describe an experiment to determine the refractive index of a small quantity of liquid using a concave mirror. So here we shall come and say that a concave mirror is placed on a table with its reflecting surface upwards. Then we shall come and write that an optical pin is clamped horizontally on the retort stand above the mirror so that its tip lies along the principal axis of the mirror. So the tip must lie along the principal axis of the mirror. Then shall come and say that the pin is adjusted vertically while viewing from above, and a point is located where the pin coincides with its image without parallax between them. After that we shall measure the distance r of the pin from the pole of the mirror is measured. So now that we have got this r, we shall now put the test liquid. So the test liquid is then poured into the mirror to a depth d. The pin is again adjusted to locate the point of coincidence of the pin and its image. The distance h of the pin above the liquid is measured. So the refractive index n of the liquid is calculated using the formula that n is equal to r minus d over h. So remember, like I told you, in an experiment they told us to describe, so they didn't tell us to derive, so you only quote this formula and you don't derive it. When they tell you to derive, you will derive, but in this case it is only an experiment, so only stop at quoting the formula. So half a mark for this reflecting, for putting the mirror on the reflecting surface facing upwards. Half a mark for the tip of the pin lying along the principal axis. Half a mark for the pin to coincide with this image, and half a mark for there to be no parallax between them. Half a mark for measuring the distance r, and half a mark for measuring the depth d of the liquid. Half a mark for this point of for the pin coinciding with this image again, and half a mark for measuring this distance h of the pin above the liquid, and a full mark for the expression which you'll use to measure to determine the refractive index. So now shall go to E Roman 2. So Roman 2 says, a pin held above a concave mirror coincides with its image at a point 40 centimeters from the table. Determine the new position of coincidence if a few drops, know this word, a few drops of water of refractive index 4/3 fall onto the mirror. So that word few drops means that r minus d is approximately equal to r. In other words, the depth of the water is negligible. Therefore, you come and remember that refractive index is equal to real depth over apparent depth. Therefore, refractive index was given as 4/3. Real depth will now be 40, and h is what they want. So h will be equal to 30 centimeters. Therefore, the position is 30 centimeters from the table, since the depth of the water was negligible. So half a mark for this, half a mark for this formula, half a mark for substitution, half a mark for the position. So that was question 2. Now we shall go to question 3. So question 3, part A, Roman 1 says, state Coulomb's law of electrostatics. Then Roman 2 says define the terms electric field intensity and electric potential at a point. So part A Roman 1, we have come and say that Coulomb's law states that the force between 2 point charges is directly proportional to the product of the magnitude, this word magnitude, of the charges, and inversely proportional to the square of their distance of separation. So that is Coulomb's law. Then here we have to define electric field intensity and electric potential. So we shall come and say that electric field intensity is the force experienced by a positive charge of 1 coulomb placed in the field. What about electric potential at a point? So we shall come and say that electric potential at a point is the work done to move a positive charge of 1 coulomb from infinity to a point against electrostatic repulsion. So 1 mark for this law, 1 mark for this definition, 1 mark for this other definition. So now shall go to part B. So part B says sketch graphs of the variation of electric potential and electric field intensity with distance from the center of a charged conducting sphere. So they want the graph inside and outside the sphere for both electric potential and electric field intensity. So let's start with the one for electric potential. Now for electric potential, inside it is equipotential, so equipotential, that's why you see a full line here, constant, but outside it is exponential. That is for electric potential. What about for electric field intensity? For electric field intensity, inside it is 0, so that's why you see that it is 0, but outside is exponential. So now shall go to part C. So part C says charges Q1 and Q2 of negative 5.0 microcoulomb and positive 2.0 microcoulomb respectively are placed at 2 opposite corners of a rectangle of sides 5 cm and 10 cm as shown in the figure below. So this is Q1 and this is Q2. Then they said calculate Roman 1 the electric potential at A and Roman 2 electric field intensity at A. So for electric potential, we shall just quote the formula, and after quoting the formula, we shall come and substitute. So K is 9 exponent 9, it is under the constants, which is 1 over 4 pi epsilon naught. Then Q1 is this. Now this is electric potential. For electric potential, if there is a negative, we put it as it is, so that's why there's a negative 5 here. But because it was microcoulomb, we have to multiply by exponent. We have to put exponent negative 6 to change it to coulomb. Then this R, if you look at this, so if you look at the diagram, for this Q1 the distance is 10 centimeters and for Q2 R is 5 centimeters. So 10 centimeters you have to change it to meters. That is why here there is 10 exponent negative 2, and for this Q2 was 2 microcoulombs, so you change it to coulomb. Then the area was 5 centimeters, so you change it to meters. Now when I use the calculator, I'll come up with negative 9 exponent 4 as my electric potential volts. Now I think you realize that we are using scientific form, so under electrostatics it is easier if you use scientific form because there will be either many decimal places or recurring decimals. Now we shall go to Roman 2. Now Roman 2, electric potential was a scalar quantity, but when it comes to Roman 2, let's see Roman 2. Roman 2 said they want electric field intensity. Now electric field intensity is not a scalar, it is actually a vector, therefore the direction matters. So let's first redraw the given diagram and we see the directions of those electric field intensities. Now they want the electric field intensity at point A. So at point A, what you do, you assume a positive 1 coulomb there. Therefore positive 1 coulomb and a negative charge here, positive and negative, there is attraction, so this is fixed. Therefore this one electric field intensity will be in that direction because of attraction. Therefore we shall come here and put our E1 there in that direction. Then between this and this, here there is a positive 1 coulomb and this is a positive charge, so there will be repulsion because this is fixed. Repulsion will be in that direction. Therefore we shall come and put it as E2. Then next we have to show the resultant electric field intensity. So to show, we are going to first reproduce E1. I think you realize that's a dotted line. Then also reproduce E2. I think you realize that's a dotted line. Then from there, I'm going to join from start to end, and that will be our resultant. So start to end, that will be our electric field intensity at A, which they wanted. But since it's a vector quantity, we also have to get the direction. So half a mark for labeling this vertical axis as V, half a mark for this area, half a mark for inside the sphere, and half a mark for outside the sphere. Half a mark for this labeling vertical, half a mark for labeling horizontal, half a mark for inside the sphere, which is 0, half a mark for outside the sphere, which is exponential. Then you have full mark for quoting the formula for electric potential, full mark for substituting this, and full mark for substituting that, full mark for the output, full mark for the correct intensity diagram. So now electric field intensity at A due to Q1 will be given by that formula, K Q1 over R1. So K is 9 exponent 9, Q1 is 5 exponent negative 6. So here we don't put a negative. For intensity we don't put a negative because it's a vector quantity. Then R1 was this, so it is squared, so we put a square there. So the output will be this, still in scientific form. And the unit must be seen, and also the direction towards Q1. We are using Q1 because that's what was given in the question. What about the electric field intensity at A due to Q2? So it will be E2, which is K Q2 over R2 squared. So come and substitute for K, for Q, and for R2 to come up with this, and it's away from Q2. Then now is to get the resultant electric field intensity which they want. So we shall use Pythagoras theory because it's a right angle triangle to come up with this expression as our electric field intensity at A. But remember, because it's a vector quantity, we have to also get the direction. So you come and say that from SOHCAHTOA, tan theta will be equal to this over that, giving you theta as 57.99 degrees. So now we can conclude that the electric field intensity at A is this in the direction this above the negative horizontal. So substitution, output, substitution, output, substitution, output, substitution, output. So that was question 3. Now we shall go to question 4. Question 4 part A says define the following terms: Roman 1 capacitance of a capacitor and Roman 2 dielectric constant. So capacitance of a capacitor is the magnitude, note this word magnitude, of charge required to cause a change of 1 volt in the PD across the plates of a capacitor. Then Roman 2, we shall come and say that the dielectric constant of a material is the ratio of capacitance of a capacitor when the space between its plates is filled with a material to capacitance of the same capacitor, note this word same, when the space between its plates is a vacuum. Alternatively, you can also define dielectric constant in terms of permittivity, and to simply be the ratio of permittivity of a material to permittivity of free space, as simple as that. So 1 mark for this definition, 1 mark for this definition, any one. You don't write both, you only choose one. So now we shall go to part B. So part B says explain the effect of a dielectric on the capacitance of a capacitor. So we shall come and say that when an insulating material is inserted between the plates of a charged capacitor, its molecules are polarized and distorted. Therefore, at the surface of the material, the charges that appear are of a sign opposite to that carried by the charge on the plates adjacent. So what does that mean? It implies that the electric field set up by these induced charges is opposing the one originally between the plates. Why? Because if you have plates, this side is positive and this one is negative, it implies that the polarized molecules will have a charge, so that if this is positive, this here to be negative and here to be positive. If this is negative, here to be positive and here to be negative. So what does that mean? It means that the intensity here, this is positive, this is negative, and this is negative, this is positive. Therefore they will be opposing. That's what they mean. So this leads to the reduction in the electric field intensity between the plates, and as a result the PD across the plates reduces, and since magnitude of charge on the capacitor remains unaltered, this implies that the capacitance of the capacitor will have increased. So in other words, inserting a dielectric increases the capacitance of a capacitor. So have a mark for this word polarized, molecules getting polarized, then the sign appearing which is opposite to that of the plates, then electric field being set up, then opposing, then reduction in electric field intensity, PD reducing, charge remaining unaltered, and capacitance increasing. So now we shall go to part C. So part C says derive an expression for the energy stored in the capacitor of capacitance C charged to a voltage V. So you come and say that at any stage of charging, V, which is PD, is equal to Q, which is charge, over C, which is capacitance. Now shall let the charge be increased from Q to Q plus a small change in Q. In that case, the graph of voltage against charge is as shown below. So it's a straight line graph through the origin. So that is the straight line graph through the origin. So you want to show Q1 and Q plus delta Q on the graph. So that is Q1 corresponds to a PDV, then Q plus delta Q corresponds to a PDV plus delta V, and the area you want is that, because that area will now be the energy supplied. So if you come here and say that the energy supplied to put an extra charge, small change delta Q, on the plates is equal to the area of the shaded strip. So that area, if you look at it, this area is a trapezium. So we shall use the formula for getting area of a trapezium to come up with the small work done, which is a half V plus delta V multiplied by delta Q. So when I simplify, this and this is 2V, but there is a half here, so 2V times a half is V, which is this, and also delta Q is there, so it becomes V delta Q. Then after that, also for the other term, there is delta V here, there is delta Q here, there is a half here, so we'll come up with a half delta V delta Q. But remember, these are small changes, this one and this one, so a product of two small changes approximates to 0. So the whole of this cancels to remain with this. But we know that V is equal to Q over C, so that at the beginning, that means that when I substitute for V, I'll come up with Q over C multiplied by delta Q. Why are we substituting for V? It is because this one cannot work with V when you are integrating to get the total work done. So we have to change to in terms of Q, which is the same variable as this one. Therefore, to charge the capacitor from Q equal to 0 to Q equal to capital Q, total work done will be given by this integral. So this is what I was meaning. If we had left this V here, there is no way we would have integrated, because the integration is with respect to Q. Now this C is constant, so when I integrate Q, I come up with a half Q squared, which is this, and this C is maintained from 0 to capital Q. So when I substitute limits, I'll come up with capital Q squared over 2C. But I know that Q is equal to CV, therefore the energy stored in the capacitor is given by that. So I'm going to substitute for Q here to come up with a half CV squared. Now why are we expressing our energy in terms of CV squared? Because in the question, if you look at the question, so if you look at this question, you are only given C and V. Therefore, it means that you have to express the energy in terms of C and V. So half a mark for this area, half a mark for this assumption, half a mark for this substitution, half a mark for this definition of work, total work, half a mark for integrating, half a mark for the output, half a mark for substitution, full mark for the required expression. So now shall go to part D. So part D says, in the figure below, C1, C2, C3 are capacitors of capacitance 3 microfarad, 2 microfarad and 2 microfarad respectively, connected to a battery of EMF 100 volt. So this is a diagram arrangement. Part Roman 1 says, calculate the energy stored in the system of the capacitors if the space between the plates of C1 is filled with an insulator of dielectric constant 3 and the capacitors are fully charged. So we have to first deal with this dielectric constant. Therefore we shall come here and say that the new capacitance of C1 with the dielectric inserted is given by C4 equal to dielectric constant multiplied by the capacitance with free space. So dielectric constant is 3, capacitance was 3, so we'll come up with 9 microfarad. Then next is to combine C2 and C3 which are in parallel. When you look at this diagram, these two capacitors are in parallel, so I'm going to combine the two and come up with that 2 plus 2, which is 4 microfarad. So capacitors in parallel are got by adding. Then therefore the effective capacitance of the whole system. Now when I combine these two, I'm going to come up with this. Let me come here. So what I have done, I've combined this into one capacitor. Now I have this capacitor C1 and this capacitor C4, C5, which are in series. So capacitors, two capacitors in series are got by product over sum. Therefore shall come here now on our calculation and say that the effective capacitance will be equal to product over sum. Which will give you 2.7692 microfarad. Like I said, in physics 2, it is not allowed to leave your answer to in fraction form. So if your answer is in fraction form, just know that you are going to miss that mark. Therefore, always remember to give your answers in decimal points and don't leave them in fraction form as long as you are dealing with physics. So now we shall come and say that energy stored in the system of the capacitors is given by a half CV squared. So C is that, you have to change, because this was microfarad, you change to farad. Then V is that, so the output will be that. So also under this topic, answers are easily expressed in scientific form. So half a mark for substitution, half a mark for output, half a mark for substitution, half a mark for output, half a mark for substitution, half a mark for output, half a mark, full mark for formula, full mark for substitution, full mark for output. So now shall go to Roman 2. Roman 2 says, account for the change in energy stored by an insulated power plate capacitor when the plate separation is doubled. In other words, when it is increased. So when the separation of the plates is doubled, work is done in pulling the plates apart. Therefore, this work done is stored as electrical energy between the plates of the capacitor. So they wanted us to account for so that is what they wanted. So that brings us to the end of this video. Thank you for watching, and as far as beginning of term 3 is concerned, we have dealt with A-level math paper 1, paper 2, A-level subsidiary math, A-level physics paper 1 and paper 2. Now we are going to O-level math paper 1, and we proceed until we finish paper 2 math O-level, and also paper 1 physics O-level and paper 2 physics O-level. So this brings us to the end of this video. Thank you for watching, and be reminded, and if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. Otherwise, thank you for watching, and also if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.